Hello, everybody. I'm just gonna do a rundown of my data science for my data science interview tomorrow. Um, Quick rundown. I'm gonna make this video pretty short. So, starting from machine learning, linear regression, a very simple model here, linear regression. Um, Basically, linear regression is y equals y equals Basically, linear regression is y equals intercept plus slope times x. X is the input data. Slope is the one of the feature, and then the intercept is the bias here. So bias, and then slope here, and then we're gonna predict the y hat. And so, what linear regression assumes is that the correlation between features are not correlated or uncorrelated, meaning now for polynomial regression models, there's more than one feature, which is theta 2x, theta 3x, and so on and so forth. So we're adding all the way to theta n, xn. So on each feature, we're trying to we're trying to optimize these data values and output a y. And so we are predicting this, and then the evaluation metric we're going to use is MSE, which is mean squared error, or RMSE, root mean squared error, or mean absolute error. And so with regression models, it's very common to see like these kind of error metrics, like we square it or we root square, or like just absolute value of these two. And then in the end, what we can get here is we're trying to minimize this error, and the whole point of linear regression is trying to fit a straight line into these data points, the best fit line. So we can minimize the distance between these data points and the line, which are the variance the error captures, the model that the model captures the error. So since we have this now, from here, what we're trying to do is now when there's errors here, these error values, they are assumed that thetas are going to be they're going to be so multicollinearity is the problem here for linear regression, is because there's a lot of features in real worlds that are going to be correlated to each other. Like number of house prices and number of bedrooms are going to be positively correlated to predict the price of the house. So it's important to do a lot of feature engineering for this model. But the good thing is, the simpler model it is, the simpler the model, the higher the interpretability. We can interpret really easily. Complex models like deep learning models, XGBoost, those are hard to interpret, so it's black box models. And there's a variance bias trade-off, which for the higher more complex models, now this is like the graph of variance bias trade-off, and the more complex model we use, it's harder to look at, and the higher the variance risk is. The simpler model is going to be higher bias, lower variance. That's that. And then eventually, so in overfitting, in machine learning model, the machine learning overfitting happens because the training data is learned too much by the model, so the model learns it way too much. So the model learns all the details about the training data that when it sees the test data, now it performs really bad. For underfitting, it didn't learn enough information about training data, so it also performs bad in test data as well. Now logistic regression. Before we go there, lasso regression is L1, L2 is ridge regression, and the way that machine learning models train, how they are trained, and learning their weights is once they compute, once they have their own algorithm for each model, they have, when they do this, we're going to try to minimize this. So we take the partial derivative of each feature here over in terms of each input. So we do this for every single feature here, and we subtract the partial derivative for this for each of these features. So for intercept, and this is for d1 dx, and from here, the reason why we're subtracting is because we want to tweak it. And how do we know we're subtracting it? Well, linear regression, if you look at this function here, it's a bowl shape. And towards, we know that this we want to minimize the error here. So this partial derivative, it tells the direction of which way we need to go. But then we don't know how many steps we have to take in order to go down to this bowl into here. So this is like a bowl, and this is a bowl shape, but this line represents error. And so if we look at and this is a representation of a 2D model, so it assumes there's only 2 features. But in real world, we're having 20 features to predict one value here for house price, for example. And for these 20 features, we can't really draw realistically 20 dimensioned pictures here. So what we do is we just take the partial derivative. We know the direction and which way to go to minimize this error. And there's learning steps called alpha. This alpha needs to be picked through hyperparameter tuning to know which value alpha is going to be the most appropriate value. So now, when we multiply this by alpha, we know how much step we need to take and which way to go by partial derivatives in order to tweak this value, theta 0, theta 1. And now, after we have this, we're going to have a good set of weights here, and then now we use this weights to do matrix multiplication with unseen data, test data, and output a value that minimizes the evaluation measure, such as mean squared error, root mean squared error, mean absolute error. And now that's the algorithm. So for logistic regression, it's linear. That's classification. Linear regression is a regression model that predicts continuous values, like decimal numbers like 203 and stuff. Linear regression changed itself. Actually, so L1, which is ridge regression, lasso regression. For the error function here, and when we do the weight tweaking, let's see right here, partial derivative theta 0, theta x0. What we do is we kind of like multiply or add. We add like a absolute value of something. We add a absolute value of some sort of like value here, and then we add the weights here to make some regularization changes. So regularization in machine learning is another way to overcome it's a way to overcome overfitting. So when overfitting happens, again, it's because the model is learning the parameters way too well. It's learning the data, the input set data way too well, that there needs to way to chill the model, to calm the model down by adding more weights, tweaking the partial derivative, how much it needs to tweak the theta. So it adds like some sort of value here for L1. It adds an absolute value here, which also we can tell by this L1 value which features are not important when we're trying to predict the y hat. For L2, we're trying to like square some sort of value. So the y hat, it tells us like it doesn't eliminate what feature is unimportant. but it still leaves if the feature is unimportant. So it's a feature selection method for L1 can be used for feature selection method as well. Now from here now, linear logistic regression is using logits. It's using a sigmoid function, which uses the linear regression model here, y equals, so theta 0 plus theta 1x right here. And this gives us a value ranging from -1 to 1, which is what sigmoid does. And if you draw a graph here, I think -1 to 1 is tangent function. So I think this is 0, 1, 0 to 1. I'm gonna review it later. But anyways, this is the threshold for the logistic regression model to predict as a negative or positive depending on the threshold. You can move around this threshold when you train this model here. And so the log odds is really important in this for this model, and the way it's trained is the same, literally the same as linear regression model. Just to see the notes here. Oh, and also for training machine learning models, there's a thing called epoch. Epoch is not only in machine learning, also AI when you train AI models. We always use it. Epoch means one route, one cycle of learning the training set. So no matter how big the training set is, like let's say we have 2 billion rows or like 10 petabyte of data, we're like using this training data to for the model to learn the weights, to tweak the weights, and that's one epoch. So learning once of this training data is one epoch. If you have normally people go like more than 50 epochs, but if you write too much epochs, the model is going to learn the training data way too much, which causes overfitting. So also tweaking the this is considered also hyperparameter. Also writing. Using the appropriate amount of epochs is important in ML. And so also the threshold is really important when you train models. For example, the threshold that I was talking about in logistic regression is if it goes over the predicted probability, predicted prog, as more than 50%, then it's going to be, it's going to be classified as fraud. If it's lower than 50%, then let's say we're classifying it as not fraud, like just regular transaction. If we talk about credit card transactions, then we can lower this bar to like 30%. The threshold tweaking is really important, and from this we can also know if the model is performing well or not. If it doesn't perform well, there's hyperparameter tuning, or there's multiple things you can do. First is you got to identify if it's underfitting or overfitting. Depending on this, we can go ahead. If it's overfitting, we usually want to simplify the model. Meaning we're going to use a simpler model, like random forest instead of crazy deep learning multi-neural perceptron models. Now there's another way to mitigate overfitting. It's to do feature engineering again. So if you think about it, the better quality data is more important than a perfect model that fits the data. Because if you think about it, if there's a really simple model, basically just very, very simple, but the training data has really good quality, then the model can still perform in a baseline level. On the other hand, if the model is really complex, really good model that has a perfect architecture, but the training data quality is really bad, it doesn't even represent the real world data, then the model is not going to learn anything. So the most important thing is feature engineering. in overfitting or underfitting problems. Usually, if it's overfitting the feature, there's too much features, there's too many values that the model's learning. So maybe feature selection, redoing feature selection would be a helpful way to do it. Maybe one of the residuals or like the features are maybe not following the bell curve normal distribution. They're not normally distributed. So this could also be a problem. Normally, machine learning models they learn data sets really well when the data is bell curved. So there's a lot of functions that you can like transform your data into normal distributed data. The whole point of existing feature scaling methods like min-max scaling and scikit-learn, standard scalars, and these kind of feature engineering tools, these are really important. These always comes out when it comes to training models. So these feature engineering skills are really important to actually apply in features. And one of the LinkedIn posts actually I saw a post where instead of having a feature which is a numeric value, it's the model learns it better when you transform this numeric value. Let's say there's numeric values ranging 0 to 200. You split this into boxes and then name them like low, medium, high, super high. Like these discrete values learn better in models than these continuous values. I saw one of the LinkedIn posts like that, and I think that's also very insightful to talk about in interviews. What else? Oh, when it's underfitting, it's better to gather more good quality of data, adding more rows. For overfitting, it's not good to gather more data because that's more information for the model to overlearn. So that's that. And now we go to support vector machine. So support vector machine is like, kind of forgot what it does. Not really important in interviews, but I just have a basic idea where it's hyperplane, so meaning like each plane represents a feature. And there's so many things here, so many features in real world data set. It could be ranging from like, one to like a lot. And each hyperplane, when we cut it in half, we have these data sets that are that compose in the space here. And what we can do is we can see these data sets and draw another hyperplane to make a classification model here. So yeah. And there's a lot of hyperparameters in support vector machine. Yeah, there's linear support vector machine. There's non-linear. Yeah. So now next is decision tree. Decision tree is you don't need a feature scale. You don't need to scale the features for decision trees. Is because decision trees are more like a binary answer, yes or no kind of thing. Now the evaluation metric, one of the hyperparameter, so when making predictions in decision tree, there's a thing called Gini impurity. Gini impurity is when what it's used, how impure or pure there is when after it makes a decision. So if this side only contains one class, and this side also cleanly makes 50-50 class, in a good classification model, the Gini impurity score will be low, because the impurity means it basically means it did a terrible job in classifying binary classification or multi-class classification problems. Uh, regularization hyperparameters. Oh, so also there's another evaluation metric called entropy. It depends. Just do. I have to study about this. I forgot when to use which one to use which. But according to my notes, it says it doesn't make any big difference. Gini impurity is slightly faster to compute, so it is good in default. However, when they differ, Gini impurity tends to isolate the most frequent class in its own branch of the tree, while entropy tends to produce slightly more balanced classes. So entropy, as I mentioned, it produces more balanced classes, balanced trees here. And yeah, regularization hyperparameters. There's so many hyperparameters in decision trees. You can control how much the tree goes down, splits the nodes. The more it splits the nodes, the more it's going to be overfitting. Obviously, because like you're learning much more the training input. So you can like limit the number of leaves here, or number of or the you can also limit the number of things you put inside each node. You can also put on weights when you think one class is more important than other class in imbalanced uh, imbalanced data sets. Like credit card fraud is like it's very well known problem in imbalanced data sets, because most of the transactions in everybody's credit card is valid, but there's only like a couple of them, like maybe out of 100, there's only 5 that are flagged as fraud. So in order to train the model with these kind of data, we have 95 rows, 95 samples to teach the model that it is not fraud. But then we only have 5 samples to teach the model that it's fraud. So like this is imbalanced data set, so we can use a technique called smelt. But also smelt it's creating a synthetic data set, which which we can like amplify this data set into like 95 using statistics, creating some synthetic data here. But that doesn't really represent the actual reality data. That's just made up data. But it's just one of the technique if we're dealing with imbalanced data. My favorite would be adding weights. So if we have 95 transactions that are clean and 5 that are fraud, then we can add weights, because we can add weights, for example, like 0.7. I usually do tuning jobs for this too when I assign the actual number, but just for the sake of example, I put 0.7 because this fraud is important, because the whole point of building this model is to detect fraud. So I think this detecting fraud job is important, so I'm going to put a heavier weight than the fraud. So when training the model, we can assign weights like this. The decision tree has regression capabilities, not only classifiers. Ensemble learning would be this. There's multiple trees, multiple decision trees that we can use. We gather up their outputs and we do a majority voting in order to predict the actual outcome. Now, because you're using so many decision trees, and it doesn't need to be decision trees actually. You can literally use so many other models and then just gather up, chunk their decision up, and then output into as a prediction set. So there's predictors, random samples, yeah. Now, random forest classifier is a very popular model in ML. It's because it has the capability of, when it predicts a certain value, or when it classifies something, when it does a classification job, 0 or 1, it gives like a reason of why it predicted, so it's interpretable. It gives like the top 5 features of like what causes, what can not cause, what correlates, or what like when 1 unit of their feature increases, how much this will increase, this prediction will increase. feature importance. So it outputs a feature importance. Learning rate is important, which I talked about when you're tweaking weights. And now we have PCA. PCA is a dimension reduction technique, but it's linear, meaning it captures data in a linear way. So it doesn't. If the data set is nonlinear, if it has nonlinear relationship, then PCA is not the best way to actually not the best dimension reduction technique. But it captures. But the purpose of PCA is to capture as much as capture the variance as much as possible. So if there's multiple data here, there's so many data, so many features. We basically transform this into a eigenvalue and eigenvector. Eigenvalue, and this is eigenvector. And each PCA, so PC1 is always going to have the most variance that captured. And then starting from PC2 is PC3. These are basically each feature. So basically, if you have like 30 columns of data, you're transforming into 5 columns. And that's what PC does with eigenvector and eigenvalue. It captures the variance as much as possible. And you can use this shrunk columns, shrunk feature, and train the model. And hyperparameter tuning, actually, there's grid search and random search and actually Bayesian tuning. So grid search is when you put a set of hyperparameters, you train the model with all the possible sets, all the possible pairs, meaning it takes forever. It takes such a long time. Random search is when you have hyperparameters and you select only like random pairs of those hyperparameters and then train the model. Since you're choosing random pairs in this all like in these hyperparameters, it's not ideal because when you pick random hyperparameter pairs, you could potentially miss out the best performing hyperparameter. For Bayesian training, it's a mix of these two, which is the best. And I always use this Octuna tool to train the models. Now, so taking notes. Kernel is what I need to review for support vector machine. There's other dimension reduction techniques like t-SNE, linear discriminant analysis. The nonlinear methods are like autoencoder architectures like encode decode. So we encode the training set into a smaller scale, like a tiny box. We decode it back, and that's how generative AI works. So this is a nonlinear method that I can use. So yeah, that's called Latin space, by the way. That small little post-dimension reduction. Now there's k-means clustering. We're going to unsupervised learning. K-means clustering is pretty simple. It's just creating boundary. If there's like a bunch of scattered data sets, like we have data all over here. Depending on the user input of the hyperparameters, it can divide these data sets into multiple groups and assign them group 1, group 2, group 3, group 4. In order to identify how many groups is the best group, we usually use this metric called inertia. And if you draw a graph here, There's elbow method, so when it comes here, and then there's like a slight, there's always a area where it linearly drops. So that area, that's the best performing group number, inertia. And so K means meaning like high inertia, then K. So just make sure that you don't increase the K value way too much. The silhouette value is also a very it's a very important concept here. Now we go to deep learning. There's sequential models and all these things in TensorFlow, but in PyTorch, it's more. I like PyTorch more because it's more Pythonic. From here, there's model architectures that you can use, and each of these model architecture does the exact same thing as machine learning models. It's basically just reading the training input, tweaking the weights, and then evaluating. So evaluating and then tweaking the weights, and then repeat that over and over again because this is the training loop. And then we have a test data evaluation metric here, test accuracy. And then we output this, and then we see if the model performs well or not. Basically, the idea. Just the interesting thing for deep learning is more about the complexity. So it's all about experimentation. You can add so many layers, like linear layers, nonlinear layers, LSTM layers, like RNN layers, any kind of deep learning layers you can add, and then see like what kind of output you get when you train the data. For pre-training, you're basically freezing these layers to not touch the weights, and you're only tweaking these couple layers in the end or the output layer to match it with your own use case. So if you're only trying to, like, for example, classify 10 zoo animals, then your output number neurons is going to be like 10 neurons. So yeah, number of hidden layers is all like experimentation. There's ReLU atom. These are important. The RNN is, so the LSTM models, it came from RNN. Traditional RNN does terribly because of the disappearing gradient problem, vanishing gradient problem, and exploding gradient problem. To mitigate that, we use LSTM, and then from LSTM, we have other models like GPT can perform better and all these things. And each model architecture, there's like batch normalization and stuff. It's important to know. And image classification models. And image classification, like ImageNet or ResNet, there's like pooling layers. There's more like there's strides, padding, and everything. These kind of techniques are important. I think padding is like you pad with zeros so that you maintain the dimension of the image. Stride is like you're doing like addition or multiplication. Pooling is like there's 2D and 1D pooling. And there's convolutional layers and stuff, CNNs. Yeah. I have a lot more to go actually. Keep studying. But I'm pretty sure there's going to be some questions regarding to traditional machine learning model algorithms. So I'm going to be going to understand more about I'm going to study more about the convex function. Actually try out the math for gradient descent. and maybe practice with scikit-learn datasets too. Again, oh, and the the important thing about data science projects is the problem. You need to know what exactly you're trying to solve, and the problem formulation is first. And then what you do is you gather data, and then once you gather data, you do EDA, exploratory data analysis, and then you do feature engineering, and then model training, model build and train, and then you evaluate, and then you deploy it. Right now, the current market is deploy is the most important thing. I think what's most important thing is these two: problem and gather data. If you don't know what the exact problem is, if you don't know what you if you don't have a good understanding of your own data, you will not be able to perform any of these. So I think these are the core in data. And then of course, like feature engineering and EDAs are important, but if you don't have a good quality data to start with, none of these, you will not be able to train the model well. The model will not be able to have a perfect weight to solve your problem. And yeah. All right. This is really brief summary just for myself. Just to identify, because this rundown actually gave me an idea of which area I'm lacking. So I'm going to be studying more in detail before my interview. So yeah, thanks.